Hello, welcome back. In this session, we are going to talk about exploratory data analysis, data preparation, and feature engineering. So, agenda for today, we start with EDA or exploratory data analysis. We see what is EDA, why it is important in the whole data preparation and whole model training also. And then we talk about data preparation, we talk about feature engineering, then we'll have a hands-on demo of you doing data preparation and feature engineering using SageMaker Data Wrangler. So before we build any machine learning model, we need to answer a simple but critical question. Do we truly understand our data? That's where the EDA comes in. EDA is not one-time task. It's a systematic investigation, a methodical process to explore the structure, the distribution, quality, and meaning of your data set. So let's walk through what EDA helps us to accomplish. First, it provides us a systematic investigation of a data set. We are not just looking at the few rows, we are analyzing the pattern, the structure, and the relationship in the data. Second, it also helps us in the pattern discovery. So we begin to uncover relationships and trends we don't know that exist. This often gives an idea for useful features we can engineer it later. And third, EDA helps us to perform anomaly detection. It allows us to identify outliers in our data or strange values that would confuse or mislead our model. These aren't always error. Sometimes they are insights. Finally, we get a data quality assessment. This includes missing values, inconsistencies, and data that doesn't make sense, things we need to clean or transform, or we need to drop some data before building a reliable model. This is what EDA does. So we'll go into more of EDA in the coming slides, like we go into different techniques and different aspects of EDA in the coming slides. Now we know why EDA is important. Let's talk about specific things we are trying to find when we explore a data set, right? These are not just optional, they directly influence how we clean, transform, and model the data. And the more the data is clean, the better your model training outcome is going to be. So for that, first we look at the missing values. Are there any gaps in the data that could affect model performance? If a feature is missing for too many rows, we might drop it. If it's missing for just few, we might fill it in with a mean or median or a default values. Now we look at outliers, extreme values that doesn't fit in general pattern. These might be legitimate, like a VIP customer with very high usage, or there could be some errors like a $10,000 phone bill. Either way, we need to detect them and decide how to handle them. Then we study the distribution of the features. Is the data skewed? Is it normally distributed? Understanding this helps us decide if we need to normalize or apply transformations before training a model. Another critical factor is class imbalance, especially in classification problems. For example, if you have data where 90% of customers don't churn and only 10% do, so a model might just learn to say no churn every time because it is having the imbalanced data. So we need to detect this and apply techniques like resampling or weight loss functions to address this class imbalance. Lastly, we also assess variable correlation, whether any features are related to each other. Highly correlated features might be redundant. Like on the flip side, some correlation might uncover strong predictors that are great for when we do the feature engineering. Together, these 5 components give us the full picture. They help us clean more effectively, engineer smart features, and choose the right modeling approach. So one of the first and most important tasks in data preparation is identifying missing values. But here is the thing, not all missing values are created equal. Before we decide how to handle them, we need to understand why they are missing in the first place. That's where these 3 categories comes in. So let's start missing completely at random category. This means the missing values have no relationship to anything else in the data set. They are purely random. For example, a sensor might have failed, or maybe the user has not entered a particular field, skipped in the form, right? So these are the easiest type of missing to deal with. We can just drop them or impute values without much risk of introducing bias. Next, missing at random. This means the missing data depends on some other observed variables, but not the missing value itself. Imagine a user with a shorter tenure are more likely to skip a survey question. So this is most complex. We may need to use these related variables to impute or flag the missing values. Then there is a most challenging case, missing not at random. This is when the reason the data is missing is tied to an unobserved value itself. For example, high income users might avoid entering their salary in the form. If we ignore this, we risk a serious bias. So this type of missing values requires a careful treatment, sometimes even modeling the missing values itself. So now why does all this matters? Because missing values impact the model performance. If we handle them incorrectly, we introduce a bias. That means we reduce the predictive power of our model and reduce its reliability. So that's why before we drop or fill anything, take a moment to understand what kind of missingness you are dealing with, why they are missing. Do you know the reason they are missing, right? That's very important to understand. That decision could have a major impact on downstream, especially when it comes to the fairness and accuracy of your model. So now let's talk about another foundational concept in EDA, which is data distribution. This refers to how values in data set are spread, whether they cluster around a central point or they spread evenly or form a skewed or multi-peaked patterns. First, we use EDA to identify the skewness of data. Many ML algorithms, especially linear models or logistic regression and even some neural networks, assume the data is close to normally distributed. If the distribution is heavily right skewed or left skewed, this can affect the model assumptions and performance. Next, distribution analysis helps us to detect anomalies. There could be some rare outliers in the tail of a distribution that are either errors or very valuable edge cases like churn risk or fraud indicators. Recognizing these during EDA allows us to treat them appropriately before modeling. We also use distribution plots to assess the normalization needs. If a feature is skewed or has a long tail, we may need to apply transformations like a log or a square root to make it more model friendly. Finally, distribution helps us to guide scaling decisions. Not all scaling techniques work the same across all distributions. For example, min-max scaling works for a well-bounded uniform distribution. A standard scaler assumes a bell curve. So it's important to understand the underlying distribution before picking a pre-processing technique for our data. So as you can see from the charts, a normal distribution is systematic around the mean. A skewed distribution pulls to one side, either left or right. A bimodal distribution shows two peaks, indicating potential subgroups in the data. So these are all real world patterns and very few real data sets follow a perfect bell curve. That's why this step in EDA is so important. It ensures that our transformations, the imputations and model assumptions are grounded in the actual data. So another important issue we uncovered during EDA is class imbalance, and this one is especially critical in business applications like churn prediction or fraud detections. So class imbalance means when one category in your target variable heavily outweighs other. For example, in our Telnova example, only 10% of customers churn, whether 90% stay back. That means that we are having highly imbalanced data set. So how does it impact the model performance? What happens is when the machine learning model tend to favor the majority class, because that's where the most of data is. So the model could predict that no churn for everyone and still be 90% accurate. But that is completely useless from a business perspective. We would be missing all the customers who would eventually is going to churn. That's why we need to adjust our approach. First, we switch from using accuracy as our main metric to things like a precision, recall and F1 score. We are going to talk more about these metrics in the coming sessions, which better reflects performance in the minority class. Second, we can apply resampling techniques, like whether either we oversample the minority class or that means we undersample the majority class, or we use technique like a smart which generates a synthetic examples of minority class samples. And finally, we can use algorithmic strategies like assigning a higher loss for errors on the minority class or using ensemble models that are more robust to the class imbalance. So to summary, if you don't detect class imbalance and adjust for it, your model might be accurate but ineffective from the business standpoint. And in use case like churn, fraud, or even if some kind of a disease detection, the cost of missing a minority class is extremely high. So we need to pay attention to this class imbalance as part of our data pre-processing. So now let's talk about most challenging part you encounter in any data set, which is outliers. So outliers are data points that deviate significantly from the norm. They can appear extreme compared to the rest of your data, and if it left untreated, they can skew your model learning process or even dominate the patterns it picks up. So how do we detect outliers? We use visual plots like box plots or scatter plot to see data distribution and then spot outliers visually. Or there are some statistical techniques like a z-score to identify values that fall outside the expected range. But outliers are always in bad. In fact, some of them are incredibly important. In business context, they can represent a valuable edge cases like fraudulent transactions, VIP customers, or early indicators of churn. So for example, take the case of a Telnova. A sudden spike in call volume or a major billing error might signal dissatisfaction and could help predict who's about to churn. So once detected, we need to decide how to handle them. One option is to cap these extreme values at a threshold. Another is to apply transformations like log or square root to compress the range. In some cases, we may even choose to remove the outliers altogether, but only if we are sure that they don't carry an important meaning. So in summary, outliers can either be noise or it can be signal, which is something important we need to handle. So EDA helps us to figure out which, and once you have detected them, handling them up properly helps make your model more robust, fair, and accurate. So the final step in our EDA checklist is to understand how features are related to one another and what it means looking at the correlations. So correlation analysis helps us to detect hidden relationship between variables, and those relationships can have a major impact on both how we engineer the features or how we interpret the model performance. So let's look at the example below on this chart. One of the strongest correlation we see is between age and tenure with score of 0.72. That's expected. Older customers especially have a longer tenure. But it also raises a red flag. If both of these are used in the model, it could lead to a multicollinearity where two highly related features confuse the model or inflate its coefficients. Another important pattern is negative correlation like price and satisfaction, which is 0.63 here, negative 0.63 here in this example. This tells us that as the price goes up, satisfaction drops, which is intuitive and useful for prediction. Negative correlation like this often surface valuable inverse patterns. On the other hand, we have features with low correlation like age versus data plan, just 0.12. This likely has little predictive power and might be a candidate for removal or transformations. So including weakly related features can add noise and reduce the model ability to generalize. So the key takeaway is high correlation may signal multicollinearity, negative correlation may hold valuable inverse relationship, low correlation may indicate weak or irrelevant features. So visual tools like correlation metrics or bar charts like this helps us quickly identify these relationships and make smarter decisions about what features to keep, what to drop, or what engineer further. Now that we have completed our EDA and discovered where the data has issues, we move to the next crucial step, data preparation, specifically data cleaning. This is where we take the raw, messy, real world data and transform it into a format that's clean, consistent, and model ready. So let's break down the key components of the cleaning process. First, we need to clean and format the data. The raw data might be coming from different sources. It might have some formatting issues. The data is not consistent. It could have some special characters. So we need to make sure that the data is clean and vision readable. The next, for example, you might want to turn some yes or no into values 1 or 0, or making sure the date columns are in a consistent format, that same date format is available. Next is error handling. This includes removing duplicate rows or fixing invalid entries like negative billing or amounts, or maybe standardizing how we represent missing values. The goal is to make sure that the data set is reliable and accurate. Then we deal with the missing values, which we already analyzed during our EDA. So here we need to make strategic decisions. Do we remove these rows? Do we impute the missing values using either mean, median, or a predictive model? Or do we flag them as missing and let the model learn from that? So finally, we perform normalization, which is all about getting features on a similar scale. For example, if you have a column, the range is from 0 to 1, and you have another column or a feature range from 0 to 10,000. Some model will get confused or biased. So we need to bring them onto same scale. This is where we apply the min-max scaling or z-score normalization if the feature distribution is very skewed. So all of this cleaning works is essential. In our case of a Telnova chain prediction model example, we prepare data to ensure that behavioral patterns and risk signals are accurately captured, and that's the model focus on true insights instead of being distracted by inconsistency or noise. So once we have cleaned the data, the next and arguably most powerful step in the data preparation is the feature engineering. So if you think a machine learning as a car, a features are the fuel, right? Well-crafted features can transform a mediocre model into a highly predictive one. So what exactly a feature engineering is all about? It is the process of creating new features from your existing data. They aren't just random columns. They are meaningful signals that help your model to detect useful patterns in customer behavior. For example, rather than feeding in a raw billing and tenure values, we might create a features like average monthly spend, which captures the customer value for more intuitively. So this helps the pattern recognition. It allows machine learning algorithms to uncover non-obvious relationships, like how a combination of frequent support calls and high monthly charges might increase a customer churn risk. And there is also another aspect. A proper feature engineering amplifies model accuracy. You could spend hours tuning a model, or you could improve your features and get better performance in minutes. In most real world applications, feature quality matters more than model complexity. So lastly, the feature engineering is where domain knowledge really shines. So you need to have an understanding of the business, whether a telecom churn or a fraud detection or a medical diagnosis allows you to build feature that reflect how real decisions are made. Model doesn't know the business, but you know the business. So in short, feature engineering is about turning data into insights. It is basically helping the model to uncover the patterns which is not obvious in the data. That means you are actually enabling the model to be a domain expertise. It's where human expertise and machine learning intelligence meet to build a smarter model. Now let's look at how we actually engineer features in practice. What are some of the techniques we use? These techniques help us to build a meaningful, features which could enhance your model performance. The first technique is binning. We take continuous variable like age or income and group them into categories. For example, instead of raw age, we might use groups like 1825, 2635, 3650, and 51 plus. Why? Because certain age groups may show higher or lower income churn rates, and the model can now learn the pattern more easily. Next is interaction features. These are combination of two or more columns that might reveal deeper insights when used together. For instance, data usage multiplied by price sensitivity might flag high usage customer who are also price conscious, a potential churn risk. On their own, these columns may not say much, but together they tell a story. Then we have a time-based features. These are created based on date or time intervals. For example, day since last support call, contract remaining months. These reveal a temporal pattern such as customer nearing contract expiration or recently having service issues, which are strong signals of churn. Another essential technique is one-hot encoding. This is how we convert categorical variables like a plan type into numerical form. So like basic, premium, family plans become three separate binary columns. This helps us the model to learn churn behavior for each plan type individually. Finally, another technique we use called aggregations. This means creating a feature that summarizes customer behavior, something like average monthly data usage, call frequency. These metrics helps us to understand long-term trends in customer engagement. So together these techniques turn a raw customer data into a predictive insights. So in case of Telnova, this means that we can identify easily the churn risk, segment users more effectively, and drive a campaign which are specifically targeted for that customer who was going to churn. So all before even we train a model. Okay, so to start with, our first task is to do the data preparation. What we discussed just now, we have to do exploratory data analysis, data preparation, and as well as feature engineering. So we are having very small data set, so we are not doing extensive feature engineering, but I want to show you like how we can do using data wrangler. So to start with, you can go to the SageMaker AI, you can click on Studio, you can open the Studio notebook. Between one disclaimer, if you are using SageMaker AI, it is going to cost you. So as soon as you are done with your testing out, please delete all the resources so that you won't be billed for the resources you are consuming. And all the code I'm using is actually I'm using from this SageMaker end-to-end workshop from AWS. This workshop is a little bit older, so I have to do some changes to this workshop. For example, this doesn't include the ML flow where you can log all your experiments, and then if you are using a deployment, it doesn't include serverless deployment. So so you might have to do some small changes, but it works. But most of it, the code which I'm going to demonstrate, I'm using from this workshop. So you can also clone this workshop repo, and then you can start using. You can also start using this one. To start with, when you click on the SageMaker Studio, it opens the SageMaker Studio. This is how the SageMaker Studio looks. We are going to walk through each of the sections as and when we do the sessions. But in this session, we'll focus only on the data wrangler, where we are going to do the data pre-processing, and then we are doing EDA, and then we are doing feature engineering, right? But to start with, click on Jupyter Lab. You can run a Jupyter notebook here. You can open a Jupyter notebook, and also the data wrangler runs in the SageMaker canvas. So you have to start the canvas and click on open canvas. First, go to our first notebook, which is data preparation. Here, what we are going to do, this is all initial. You can just go walk. This code is available in the GitHub repo. We're installing the dependencies, and then I'm going to come back to this section of the code again later when we do the model training. But for now, we can focus that we are creating a bucket here with the prefix XGBoost churn. We are actually getting the Docker image for the XGBoost model, which we are going to use in the later sessions. That installation we are doing it here. So I'm downloading the data from this particular site where we are having test data. All the telecom churn data, we are going to use the same data here. And then just one quick thing, you can add a no check certificate here so that you don't have the problem with downloading that particular from the site. It won't be blocked. And then once you download, we unzip the data, we extract the churn.txt from that, and then we move this to this bucket. So for now, I have moved this into this bucket, and I renamed the txt to .csv file so that I can import the data wrangler. Once I'm done with this, then I'm going to initialize the SageMaker, get the SageMaker role. This is my URI processed. So we'll come back to this notebook later, but for now we'll go to the data wrangler. To go to data wrangler, you need to click on the data wrangler here, click on open canvas, it opens. So you can click on data wrangler here. Once you come here, you can import and prepare. You can click on tabular here. You can select the data you want to. In our case, it is a raw data, so you are going to click churn.csv and then import the data into data wrangler. So I have already imported the data in data wrangler. I have done both things, where I have done extensive feature engineering in one data set, which I'll show you. The data set which we are training is this data set. This data set we're training. You can see that as soon as you import the data, you can actually change the data types. The first thing we are doing, this is like a visual drag and drop. You can drag and drop different options we are having. So first thing we are doing is, this is our source data. Then after that we are doing data types. There are few data types which we want to change. For example, there was a area code. So the area code was string, and then the phone and all some few data types which were long, I made them a string, So those things I have modified. Then after that we can run the EDA. If you can click here, you can click here and then say get data insights. You can run an explore data analysis on the data. So I ran this analysis on this data. When you click on this, it runs this analysis. It tells you how many features you are having, how many rows you are having, how many missing data, how many rows are missing, what the different your data types are there. Then you'll have your feature summary. And then it also shows your the duplicate rows. It shows your anomaly scores for each one of them. It shows the target columns. It also runs a quick model on your data, sample data set, to check how good your prediction. You can know in upfront whether what would be your F1 precision and recall for the data. I'm going to talk more about what is accuracy, what is a precision, F1 recall, AUC in the upcoming sessions. And then apart from that, it also gives all this confusion metrics. Of course, I'm going to talk more about this in upcoming sessions. For now, we'll focus only on the data analysis and then data preparation, and then this also you can also see whether is there any correlation between some features, and then how the data is distributed across for each feature. So it does a full analysis of your data. You get some just like getting a sneak peek into the data you are going to train, you are going to prepare. Then after you have done that, you can go back to your flow again, data flow again. So there are some columns which might not be required for your data preparation, so you are going to drop those columns. For example, I am dropping the phone number, day charge, because these columns are not going to make any difference in my prediction outcome. My purpose is that I want to predict a particular customer is churning out or not, right? So these attributes will not make difference. So I am going to drop these columns, and I am also doing some one-hot encoding of my churn attribute, churn feature. You can see here that to do one-hot encoding, I can actually select Python pandas here. I can write my custom code here. So I'm getting the pandas, and then I'm using this simple code snippet to do a one-hot encoding on my churn feature. Apart from that, it also provides you a lot of other features. Maybe I have another data preparation I have done here for different data set. Maybe I can walk you through that. So even if you want to do an encoding of the data, whether you want to the scaling of the data, or you want to create new features out of existing data. So all of them, all you can do is kind of a very visual. Maybe let me show you one simple example of how to do that. And this is taking time. Maybe let me go back to our old one. So you can actually go here, data here. You can add your transforms. You can add your custom transforms where you can put your custom code. You can actually encode categorical data. You can do the balancing that we discussed about smart analysis, smart technique, where when you have a data being imbalanced, whether you are doing using random oversampling or undersampling or smart technique you can use. So and then any whether grouping by columns or managing columns or any splitting of the data. So all these things you can do without, these are no code solutions where you can without any code you can do. Once you are done with this, you have got multiple options. Either you can export the data into the S3 bucket like this here, or you can export you can click here, you can export the data into an S3 bucket, or you can create an export into a SageMaker, a Python, a Jupyter notebook, or you can also create a SageMaker, a pipeline out of it, so that you will have the ready-made pipeline and everything. But in this case, I am actually exporting this data to S3. So moment I run S3, it is going to export the data. It is going to run all this analysis. That is going to drop the columns. It is going to do one hot encoding on the data and then export the data to an S3 bucket. So that data is going to be over here. I'll go to the output folder here. Sorry, I'll go to data folder. In this data, I'm going to put the processed folder. Within the process folder, now I'm having the data. This particular CSV file right now is properly processed. It has got all it dropped all the duplicate columns. It dropped it does a one-hot encoding, everything, or any other transformations I have. It has been properly processed. Now this data is ready for training, right? But before we train the data, we cannot use the data as it is. We want to do the data splitting. We want to split the data into the training data, a test data, and validation data. That's what we are going to here. We are going to create three files: train.csv, validation.csv, and test.csv. So we are going to we are going to use these functions to split the data into train, validation, test. Typically it is going to be like 70, 20, 10% of it, like 70% data we use for training, 20% for the validation, 10% for testing, right? So that but the key thing is that the model should not see the test data during the training, so that it's something like a validation data, something like a student is practicing with something like a mock questions before he actually write the exam, right? Test data like actual exam where the student takes exam. So similarly, we create a train data, validation data, test data here. Once we are done with this, we are going to store the train data, test data, validation data in different folders. So this is our test data, this is our train data, this is our validation data. So by end of this phase, we have used SageMaker Data Wrangler to do the data pre-processing. We have done the feature engineering. It is a no-code solutions. So now we have the data which is readily available for us to start building the model and train the model. So we'll see how we are going to train the model with this data in the upcoming sessions. So now that we have completed our data preparation, we did the EDA data preparation and feature engineering, we are ready to train our model. So that is what is going to be the focus of our next session. So see you there again in the next session.